It's great to be here in South Korea finally and see you on this side of the Pacific. And congratulations to the KSCE for the 70th anniversary. And I feel very honored to have been invited to speak, also to be featured this afternoon with all the other speakers that were before me. I have to say I love the vision of the KSCE nexus of digitalized infrastructure for future lives. I think for the next 30 years, that is certainly going to be a big focus and kind of a change for us civil engineers, but an important one so that we can continue to contribute to society. So I agree with the Minister of Construction and the former Secretary General of the United Nations that the Korean Society of Civil Engineers, the civil engineers in Korea, around the world, are really making important contributions for the lives of our fellow citizens. And that makes me very proud to be part of the community of civil engineers globally. But then, of course, as they also pointed out, I agree with them that we face very formidable challenges for our future that we have to play a big role in addressing, as Professor Choi also pointed out, because we use the most materials in the world and we affect many other emissions through our buildings and infrastructure. So we have to get better. Even though we create a lot of great buildings and infrastructure, we still have to get better. And that's why I titled my talk, Digital Strategies for Creating High-Performing Buildings and Infrastructure. Because of two reasons. Because without digital strategies, we will keep producing just isolated examples of good buildings and good infrastructure. But we have to create every building, every infrastructure as high-performing as possible. And I use the word high-performing to really include sustainable, resilient projects that are culturally, environmentally, socially, and of course also economically viable today and in the future. That's what I mean by high-performing. So I have not found a way of scaling any practice to many projects unless it is digital. So we have to really speed up the digitalization of our industry. So we teach the computer what we know to do so it can do that, because we have so many more new things to do that also the previous speakers highlighted very well. We have to create new knowledge. We have to deploy that new knowledge much faster than we have in the past deployed new knowledge. And for that, I also will emphasize a strategy of integration. Integrating project teams so that the best knowledge is always available for a project, but also integrating government, academia, industry for the generation of new knowledge, integrating the older and younger generations for the generation and application of knowledge. Those are, in my mind, two important approaches we have to have: digitalization and integration. The work I will present was done really in the context of the Center for Integrated Facility Engineering at Stanford University. So I have to thank my colleagues there, students, for really making that work possible. And some of the points are also summarized in that book that's featured there on the title page. So walking around Seoul yesterday for the first time, I saw many remarkable structures, and we see also many remarkable structures around the world. We see many examples of high-performing buildings. Some are created extremely fast and flexibly, like the Gigafactory in Sparks in Reno, or Sparks by Reno, Nevada. Highly environmentally sustainable, water and energy positive, sustainable and high economic return, or just very impactful because of their size, like in my native Switzerland, the longest railroad tunnel. But we have to get more of these types of buildings, as I already mentioned. So how do we get more of them? How do we make every building high-performing? And of course, technology will help us because it allows us to do things that we haven't done before. And So in that sense, technology will be extremely important because, as we heard, we have to do many things that we don't actually know yet how to do. And there is really an incredible number of technologies that are emerging. Just to name a few, many mobile technologies, cloud technologies, technologies around location, dimensional control, scanning, understanding basically the real environment in digital sense, machine learning, artificial intelligence, robotics, additive manufacturing, Internet of Things, virtual reality, augmented reality. Each one of them is actually already a big deal and could have a big impact. But we hear every day about advancements in all of them, and together they will really enable a very different future of civil and environmental engineering. So technology will help, but it's not enough. We also have to have a strategy and method. So I will introduce a strategy and method that we have found is very helpful to creating more high-performing buildings, and then share examples of advancing digitalization so that we can go beyond the current limits of performance for our projects. So we have to start first with what we need to achieve. How do we know that a building is high-performing or a bridge is high-performing? How do we differentiate one from one that's not so high-performing? So we have to define characteristics for high-performing buildings. And when I use buildings, I really mean buildings like we're in, but also infrastructure as a general term. This is something that's actually been a bit of a surprise to me in my career. I've had the pleasure over the last decade to work with well over 2,000 professionals to advance their knowledge through professional education around the world. And what they struggle the most to do is to define for their project what is actually high performance. What are the objectives for the projects? It's really surprising, but that's what we have found. So we, in this book, Integrating Project Delivery, defined 4 categories of high performance, focused on the phases and the key stakeholders in these phases. First of all, a building or infrastructure has to be usable. Otherwise, what's the point? If it doesn't support its users in the health and safety, functionality, many other features, I think for me, a building that is not usable is really wasteful. It also has to be buildable because, well, if you don't build it, then it doesn't exist, doesn't help the user. And there we have the classic objectives from safety, schedule, cost, and quality. And it has to be operable. The people running tunnels, running hospitals have to be able to do so, again, safely, and as we heard before, with efficient energy and water consumption, but also efficient maintenance and operation procedures. And it has to be sustainable, economically, equitably, socially, and ecologically or environmentally. There's lots to do, right? You can see very few projects can say we are performing really at a very high level in all of these aspects. And that's why we need to integrate the knowledge of all the project team members and support them with really the best tools possible that we can think of, that we can make. So now that we know how to define, how to recognize a high-performing building from a not so high-performing one, what strategy should we use to get one? As we were working on the book together, as I was working on the book with my 3 co-authors, we really thought about this very hard because we wanted to create more high-performing buildings. So what would be a strategy for a building so that it would be more likely to be high-performing than not? The best strategy we could think of was that it needed to be a building for which the building systems are integrated, work together, are synergistics. That also goes for a tunnel, goes for a bridge, and so on. We can understand the integration through computer models, not only, but certainly one important way to understand it here, the set of integrated systems for a large hospital in California. So then how do we get a building that has integrated systems? Because that's what we have established is the best strategy for high performance. It means really that we need to integrate the processes, the workflows that create it. And this is quite a departure from what I see around the world, where I see many fragmented, isolated processes, siloed processes, as we say in English. And so this is quite a change that we have to still work quite hard, I find, around the world to make happen in our industry. Because it's crazy to think that separated processes would create miraculously a building with systems that happen to work together very nicely. So to create integrated processes, we really need to ask the project team to make that happen, which also becomes an important part of creating an integrated organization, which is, of course, the best strategy to create these integrated processes. Because again, if we silo each of the disciplines like we still often do in many parts of the world into, by themselves, then we make it very difficult for those organizations to create integrated processes. So how do we make sure that an integrated organization works well? And here, I guess I should have shown this example. We have to really carefully design, right, how an organization works on a project. Not just think of it hierarchically, but also think of it how to make the different disciplines work together, put the decisions to the lowest level, as the organization structure tries to show here for this hospital project in California. But an organization cannot do very much without good information. So we have to, again, bring the information for the different parties together so that it can support the organization. As one of my former PhD students said, the information should work for the organization. It shouldn't be the other way around, that the organization works for the information. But too often today, we still have to work for the information. And then we lose focus on creating actually a high-performing building. And for that, we really see many emerging technologies, and now tools like BIM are very common. They connect design and construction, like you can see here on this project in San Francisco. This is now very common around the world, I'm sure, also here in Korea. So basically, what we have found is a strategy of integrating information, the organization, the processes, and the technical systems gives you the best chance of creating a high-performing building. As we reflected on that, we realized that this is quite different from how many projects are done. They tend to be done broken up by disciplines, broken up by phases, and it's really kind of crazy to think that that would create a high-performing building. That will create a resilient building, a sustainable building, a building with low carbon footprint or carbon neutral. So I think we have to get out of our current way of organizing our projects into more integrated ways. This is supported also by, frameworks, legal frameworks, agreements. Sometimes it's a project team that decides, that just makes sense, we work like this. I see that happening around the world, and sometimes the formal contracts established that focus more on the success of projects, that articulate actually what performance the project team should achieve, and less on the failures. Around the world, I still see too many contracts that focus on just avoiding failure. But just avoiding failure is not yet success, right? It doesn't create a successful building just because we didn't fail. So we really have to get into a mindset of wanting to succeed for the whole project team, and we have to create the framework to do so. So what we need, we have the strategy, now we need methods to actually deploy this strategy and make it happen. And the first one is we have to create a vision, we have to create, articulate what does it mean to be high performance in tangible ways? And this is how a project team on again, a large hospital project in San Francisco defined what they wanted to achieve. This was really important. Well, they said, build a transforming hospital complex for children, women, and cancer patients to advance caring, healing, teaching, and discovering. It was amazing when I visited this project many times. You could feel in the project team the passion, the enthusiasm, the excitement to contribute to this vision from the building client. But I don't see many projects that actually do that. So we have to define what is the measurable value that allows us to really say this design of a building is actually high performing, and we have to show it publicly, ideally. We have to translate this vision into things we can measure that we help guide the project team. Again, this was the same hospital in San Francisco. This was hugely impactful to show everybody publicly on the project team every 2 weeks how is the project going? Where do we need to get better? It really galvanized them to a higher performance. To make this possible, the visualization of the current state and envision future state of projects is extremely important. And so again, BIM, but also other visualization methods, as you will see later, are very, very impactful to avoid wasteful processes, to get everybody on the same page very quickly, and to allow the vision from the design to be translated into construction. So this allows us to connect the ideas and vision of the project team and the knowledge of the project team with the performance that the building needs to have. And then on a day-to-day, week-by-week basis, we need to find ways of the different disciplines to collaborate together. We have found co-location, collaboration, collaborative sessions extremely important for this, because without the co-location of the professionals, and of course this happens not digitally as well today, we have cycles of answering questions, of creating decisions that are too slow. And we cannot create good solutions quickly enough. And we need to manage the production. We need to manage the physical production, of course, but we also need to manage the digital production. We have to see the design really as the physical production of the building. That is, of course, connected with the physical production, and of course also looking out with the digital and physical management of the operation phase. And here we can use techniques from lean construction, from production management, operation science, and it's very important for the project team to create a, this slide didn't want to load. To create a shared understanding at a very detailed level of the workflows. Without that, you cannot manage the production. So I showed here examples from a hospital project in San Francisco that was actually a public project. So it could not really use a fully integrated contract, because that's often an excuse I hear. We can't really have an integrated contract, so we can't really do all the integration that you talk about, Martin. But they were able to create the integration anyway through the means that I very quickly illustrated for these various strategies and methods. So this is what we found high-performance teams do to make their projects perform well. They follow the strategy of integration and then this method of what we call virtual design and construction, supported by building information modeling. So these are three terms that are used around the world a lot. IPD, the integrated project delivery, VDC, virtual design and construction, and BIM, building information modeling. And this is how they fit together and support each other. And we found that projects that execute in this way have a much better chance of succeeding than when they don't. We can also put the high-performance building into the center, and around it have the 4 levels of integration: the integrated information, the production management, the integrated systems, integrated processes, integrated organization, and supported by the methods that I highlighted. Sometimes we also show the VDC framework just to create an operational model for project teams like this, where we say, okay, we have to define the value that you're seeking, the performance you're seeking in terms of what the client wants and what the project team needs to achieve. And then we need to support it by how the people work together. We call this integrated concurrent engineering, supported by the right workflows and processes and information. So I suggest that, well, this is a strategy and methods that we have found over the last really 30 years of doing research at SciFi together with industry partners that creates the best possibilities for you to succeed on your projects. So I want to focus now a bit more on digitalization and emerging technologies to illustrate some of the technologies and the opportunities it creates, but also the partnerships we have been able to have with companies, thanks to our fantastic students, to advance our practices in our industry. Because as we heard all afternoon, we need to create better practices so we can achieve much, much better projects. So first one is around virtual reality, where one of my PhD students, Simge Gürgen, was able to work with the project team on the largest wastewater treatment plant project in San Francisco to make it as buildable and as usable, operable as possible. And they did this while being in home office, so everybody had a virtual reality headset and could then participate in design review sessions to make sure that in this particular case, the water treatment plant was as maintainable as possible, or to just participate in sessions, in review sessions to understand the status of design. As we see here, everybody was in their home office wearing a virtual reality headset and having an avatar being part of the same review session and shortening dramatically, right, the review cycle time to make sure that the design is as good as it needs to be. Another key technology is the optimization methods, typically multidisciplinary optimization, because our project's multidisciplinary. Here I want to share research by Filippo Ranalli together with our longtime partner DPR Construction and their project partners. Because, right, unless we optimize our structures, we're not using our resources well. We're wasting resources, and we just heard that, well, we simply can no longer afford that. But today's methods don't really allow us to optimize the structures we create, because the data and the knowledge is too fragmented, and we haven't yet formalized the different analysis and design methods. So Filippo, together with our industry partner, was really able to take the optimization of a structural steel structure for a building to a new level. Not just optimizing for minimum weight, but optimizing for minimum material, fabrication, and erection cost, considering all the code requirements and considering all of the and detailing. Really integrating the gravity, lateral system design, and detailing to create an optimal steel structure for a good-sized office building, for example, that you would find in a downtown area in about an hour. So basically, he taught the computer everything we know to do, so it can do that. So now the structural engineer can contribute by saving 10 to 20% of material fabrication and erection cost, because we have 40 to 100 times faster structural design, so they can actually work on more projects. We have higher structural safety because of doing more calculations, and we can look at thousands of scenarios instead of one or two. And now the structural engineer becomes a very different partner in the whole ecosystem of architecture, structural engineering, and construction. But if we don't connect, right, the design and the construction professionals, we cannot get access to the data, then we cannot create this kind of optimization. So we have to not only digitalize, we have to also integrate. But if we don't create this digitally supported integration, we will keep wasting resources. It's as simple as that. And we simply cannot afford that. But this kind of optimization can also be applied to scheduling of construction projects, because the schedules of construction projects commit huge amounts of resources, right? I mean, it's, if you think that labor costs are, it varies a bit around the world, but say 50, 60% of construction costs, it's, construction 10, 12% of GDP. We're talking, 5, 6% of global GDP are committed by construction schedules. And it's really also crazy that we create typically about one schedule per project. We have one and we go with it. We do not optimize it. So we have created in our lab a method to optimize construction schedules by teaching a computer the basics of construction so it can do the simple things and we don't have to enter things into the computer again and again. We basically automate the things we know to do so that the construction practitioner can focus on exploring different strategies, different combinations of resources to really find the optimal schedule for a particular project. So this has turned into a startup that is now on the market with a tool called Alice that has been applied for building and infrastructure projects. For example, on this large road project, the construction team was a bit optimistic in its planning, and as they got into the project, they found that they were going to have a 128-day delay, which of course would have been very costly. By modeling not only this road in 3D, but also by modeling the construction processes, they could then automatically explore actually really millions of different ways of building the project and find the best ones. So you can see here on this time cost chart, on the horizontal axis, you have the duration of the project, on the vertical axis, the cost of the project. Because you have the quantities right from the BIM, the quantity of materials, you have the resources in your schedule, so you basically create an integrated model that has cost, schedule, and scope connected. And you can see on the upper right the baseline schedule they had. So a point is a particular schedule, right, which leads to a particular duration and a particular cost. And by running many strategies, different strategies with different resource combinations, they were able to dramatically shorten the time, as you can see, going from right to left, and also the cost of the project. So you can see there was dramatically better solutions possible. Those could only be found because people with different knowledge could sit together and were supported by a tool that automated the basic calculations at a large scale and allowed them to then optimize this schedule. The same was applied for a project with a road project with a bridge, where they had faced significant design changes and still wanted to finish the project, of course, as quickly and as low cost as possible. And here you can see the project team again evaluated many different strategies for creating a better schedule. This would be a whole hour to talk about all the strategies. I just want to highlight the opportunity here to use the knowledge of a multidisciplinary team supported by good tools to create schedules that are, again, dramatically shorter. If you compare the starting schedule here with the final schedule over here, and also dramatically cheaper if you compare this cost with the cost that they were able to achieve. So optimization methods allow us to employ the resources, material, and labor in the best possible way. It's certainly a strategy we must employ if we want to build sustainably and high performing. Another method that is becoming very popular in the US is to use offsite fabrication or prefabrication. But then this creates a challenge of logistics. You have to now connect the factory, which has its production schedule, with a site which has its production schedule. And you want to also have efficient logistics. And that's where we have seen challenges on projects, and this is work done actually by one of my Korean PhD students, Eugene Lee, who is now a postdoc in my lab. And she worked with, at the time, Katera and Digital Building Components, and now with the Microsoft Data Center Group to continue to expand these methods. Basically, what we found as we talked to companies that use this offsite fabrication is that the people, the logistics people, were stuck between, the factory people with their objectives and the site. And there was like a fight, the trucks are not loaded in the right way. And this actually added significant cost to the project, taking away many of the advantages that the offsite fabrication created. We then created 2 metrics to look at the quality of each truckload, which is really the connection between the factory and the site. And we focused on the stability of the load during transportation, and also then the effort needed once the truck arrived on site to install these panels. And we asked them, so how many panels are you okay to reshuffle? And they said 17%. And we defined this metric of stack stability and said, okay, given this metric of stack stability, what is the minimum level of stability that you are okay with? And they said 50%. And then we got the data from 253 truckloads on a project. And you can see here that very few fall into the acceptable range. This was quite amazing. They knew that they had a problem, but they didn't quite know how big the problem was. Right? No wonder they were fighting, shouting at each other, because they had so few good truckloads and so many bad ones that either led to too much work on site or were too unstable and led to too much work to make them stable. So we developed a tool, again, digitalized this problem and the solution to it, which then allowed us to create automatically in 2.5 seconds instead of 40 minutes loading plans for these trucks that eliminated all the reshuffling efforts and improved the panel stability and reduced the logistics cost by 23%. So this is an example of where we have to just keep on digitizing our practices, because otherwise we create these breaks in our work and we again create suboptimal procedures that lead to suboptimal results. I'm really excited about the increasing access to data we have. And already I'm seeing a lot of data being collected and actually not so many methods to actually really do something with it. But we can finally create what I call digital feedback loops, so we can actually learn. Because that's another thing, right, in our industry. It's extremely difficult to learn because there's so many disciplines involved, the projects take long, and so how do we learn what are really good practices? But these digital feedback loops, we can actually finally learn. This particular example here is from a collaboration that we were able to have with one of my other PhD students, Yanping Wang and Clark Pacific, precast company on the West Coast. They built, for example, the Apple campus, and a startup, Versatile, that creates this IoT-enabled crane hook that tells you everything the crane is doing. So finally, we're able to see and learn exactly what is happening on a job site. So we get cycle times, not an average, but cycle times for every single operation of the crane. And we also get that coupled with video. And this becomes a very rich data set from which we can really learn how a project goes. So for example, here on this parking garage project, we saw an incredible variability in the installation of shear walls on the ground floor. The fastest was 23.5 minutes, the slowest 111 minutes. Right? And in lean construction, there's a big focus, and rightfully so, on reducing variability. But it's been very difficult to get actual data on what is the variability we have. And here we could finally see what is the level of variability we actually face, the project teams actually face. And it's crazy, right? The factor of 5 between the best and the worst operation. Same type of shear wall, same project, same day, right? And so it allows you then to see why are we slow and why are we fast in a particular case. In this case, it was the tolerance of the rebar that connected the shear walls to the cast-in-place slab. So you can start to find the specific problems that cause you to be wasteful on site. We thought, okay, well, this is the shear walls, you know, they connect with the cast-in-place structure. Maybe it makes sense that there is some high variability. But we found that this continued through the rest of the project. For example, for the different precast beams connecting to precast columns or precast walls, we again saw for all of the 3 different conditions quite different average cycle times, but also a high variability in cycle time. So it's really exciting that we finally get these data that allow us to now actually act, not only because we believe something, of course we still have that, but because we actually have data and we can then agree on a common solution. So of course we can then see where on the project we have the biggest discrepancies between how long we thought something will take and how long it did take. We can run simulations and give the project team confidence and say we could actually show this project team that they could install 7 more parts per day with a 90% chance of meeting the schedule. Because, again, we had the data to really do this analysis. Another technology that digital technology I'm very excited about is robotics, robots applied to construction. And I have to say that I was a little bit skeptical after seeing the initial tries, you know, in the late 80s and 90s in Japan in particular, but also in California, focused on construction robotics. When one of my PhD students, Cynthia Broske, came to me and said, I want to study construction robotics. But I'm quite amazed at the impact construction robotics already has, especially on the health and safety of construction work and on the quality. And I will share a few examples on this. We were able to do a construction robotics class last winter at Stanford and also together with the University of Lima, and study 10 robots applied by 11 companies across 8 countries. And so I will just show a few examples here from the kinds of robots we studied. Related to civil infrastructure, we studied this layout robot. Let's see, this should, yep, okay. That automatically lays out where things should be built. There is a drone version, and then there is a little driving robot version. When we compared this layout with the traditional layout, we found that the accuracy was improved from 50 millimeters to 15 millimeters, 87% layout time reduction, 84% cost reduction. I mean, I would say this is pretty much a no-brainer to apply this kind of robot for these types of projects. We also studied this rebar tying robot that automatically ties the rebar, especially for bridge decks. So for large bridge decks, a company called Tybot, we were able to study that with a contract in the US, Trailer Brothers, as you can see here from the slides. And when we again compared this robotic production with the manual production as we typically find it, we saw 90, well, reduction of the strenuous work hours from 90% of the work hours that are strenuous to 25%. We saw a schedule and cost reduction of 21 and 25% respectively. We saw reduction in rework from 5 to 2%, and we saw a reduction in material waste from 2% to 0%. So you can see, right, each of these practices are making projects more higher performing, more sustainable. You know, socially, because we have safer work, less likely to be injured or to injure workers, and we have more efficient work. And the example that basically continues the story is actually the first robot we were able to study, this drilling robot to install basically anchors in concrete ceilings in buildings, but could also be used in infrastructure settings. This was the precursor of a robot that has been acquired by Hilti and that is now just come on the market again a few months ago, called JBot. But even on the first application on this project in Norway, quite a few years ago, we saw that a reduction in task time, not so huge, but still 11%, but really a dramatic reduction in strenuous work, 98% reduction in strenuous work. I think that's fantastic. Rework reduction from 5 to 3%, improved accuracy from 10 millimeter to 3.3 millimeter, and basically automatically clean site. So I see robots, and especially also the collaboration of humans and robots, very much in our future to create better projects for us and, you know, environment, for society. The other thing I want to say about the robots is, as I thought about, you know, imagine 5 years of work with robots, I was thinking, who will know more about construction? The robot company or the traditional construction company? And I would think the robot company will actually know more. So I think it's quite important that those of you that work in traditional construction companies get to work with robots sooner than later. Because the data, you get the data automatically. Like when we did these comparisons, that when the students worked with the project teams around the world to do these comparisons, it was very easy to get the data from the robot companies. It was very hard to get the data about the current process. Oh, we don't really know, we have to guess, you know, we don't have the details, etc. But it's very clear, as you could see from the optimization example that I shared, if we don't have the data, we can't optimize. We can't optimize, we can't use resources efficiently. So then it's crazy for us to claim that we are building sustainably and we're creating the best projects possible. So for me, all of these methods in terms of data collection, data analysis, optimization, visualization, really come together to enable a multidisciplinary team of professionals create great projects every single time. And I hope I was able to show that to you through basically the strategy of creating high-performing buildings and through the technology that is emerging and that we need to learn how to use. That's basically what I wanted to summarize here with the last few slides. Just to remind you of the key strategies and methods that I pointed out. But we see it every day in our lives, right? When we work together and when we use good tools, we can achieve dramatically better results. And we know that, so we should actually do that for our projects. And we should do it all the time. I look very much forward to that future of construction and to working with you on making this happen.